Hello, my name is Hoyong Jeong and this is my video of mathematical software final project. The final project was to choose one of 3 problems and solve it using Python, then make a video introducing my code. Now let's consider the problem. I chose problem number 1, where we have a double integral over a function of x and y. The constraints are given as the triangle below. First, to obtain the analytical solution, I solve the problem by hand. The integral and constraint can be combined, so this is the result of the combination. Then we can simplify the inner integral, which results in a function with x eliminated. So this is the x eliminated result. Now we substitute this value to the inner integral and compute the outer integral. So after the computation, the final result is minus 1 over 120. So here is the final result. So since this is the analytical solution, we will now try to approximate to this value. If the integration problem is simple, let's say if it consists of a single variable, we can use analytical approaches to find the exact solution, like, well, I've just done. However, with problems with higher dimensional integrals, it is difficult and time-consuming to take the analytical approach. Hence, we approximate the exact solution by numerical approaches, and Monte Carlo integration is a numerical approach utilizing random numbers. It's efficient for computing multidimensional integrals, such as problem number 1. To be honest, I failed to install Scikit Monaco as in the lecture slide, so I implemented my own Monte Carlo integration with Python, obviously, and this is a link of detailed information of Monte Carlo integration. So I referred to this link for some detailed information of the algorithm we are going to use. To start with, we can intuitively think of 2 approaches of a Monte Carlo integration. So, like it says here, first is the hit and miss method, and the second is the importance sampling method. First, let's look at the hit and miss method. You first draw a figure that covers the function inside the integral, so you draw this rectangular figure. Then compute the function with random input. Compare the result with the constraints, and if it satisfies, increase the hit count. So in this case, you run the functions with many random inputs and see if it is below this curve or outside the curve. So if it is below, then you increase the hit count. After repeating this process many times, evaluate the percentage of hits. So this is the percentage of hits. Then multiply the percentage with the area of the figure we draw at the beginning. So this is the area of this rectangle. So this final value approximates to the results of the integral computation. However, this method is, well, in my opinion, hard to apply to our problem, since the constraints of problem 1 isn't on the output of the function, rather it relates to the input of the function. So let's go back and look at the problem. Yes, the constraint here is on the raw x and y, not on the result of this inner function. In other words, the raw x and y are the subjects of the constraint in the case of problem 1. So I had to take the other approach, which is the importance sampling method. The hit and miss method checked whether it satisfies the constraints after the function evaluation. However, in this method, we sample the random inputs before function evaluation. So we make a set of the candidate inputs, then multiplying the average of the results with the area of the figure, we have the value that corresponds to the actual integration. So here's my implementation of Monte Carlo integration. In Python. I went through 3 trials until I could obtain the right result. So trial 1 is a little bit wrong implementation, and trial 2 is just a simple trial to check if my implementation has the correct logic, and then trial 3 is the final accurate implementation of the Monte Carlo integration. At first trial, you can see that the error is quite big. So you see here that the first floating point value is the Monte Carlo approach, and the second is the analytical approach, which corresponds to the value we calculated by hand, minus 1 over 120. So this is minus 1 over 20. I was confused with the usage of Monte Carlo technique with dependent variables. So see here that I initialized x and y at the beginning here, and computed only one loop to accumulate the result function. However, our problem has dependent variables and cannot be combined in this manner. Generation of x and y should be separate, and computing the area of the figure should also be separated in terms of x and y. So this is wrong. This part shouldn't be implemented in this way. The second trial was just to check if the Monte Carlo method was working. So I solved the inner integral by hand. So this is the result of the inner integral. You can see that I eliminated the x and left only y alive, as we did with the computation by hand. So this is the corresponding value here. And Monte Carlo technique was only applied on the outer integral. Here, so this is the result, and you can see that the result is very close to the analytical solution. So my implementation of Monte Carlo in trial 1 and 2 wasn't completely wrong. The problem was transplanting the Monte Carlo technique into a double integral case with dependent variables. So that problem was solved in trial number 3. Finally, the third implementation, trial number 3, is the correct way to solve a problem. As mentioned in the first trial, I separated the summation process and figure area evaluation of x and y. So if we look back at the referenced link, so this equation is what I've just explained about separating evaluations. The difference of this equation and our problem is that in our case x and y are dependent, whereas in this case x and y are completely independent, so they have separate boundaries which are defined by constants that relates only to the individual variables. However, in our case, this boundary, the boundary of the outer integral, so the boundary of the inner integral is bounded with another variable. So these x and y are dependent. Let's go back. Hence, these differentials cannot be treated as a constant. So these differentials are treated as constant in this Monte Carlo. However, in our case, it can't be. So they should be modified for every outer loop. So let's go back to our code, and this So this is the portion that corresponds to the differentials in my code. Now you can see that the error is acceptable. However, in such multivariate cases, the computational complexity strictly increases. Since we now have to random sample for each variable. So the difference here is that on trial 1 and 2, I had only one sampling constant n, which is 10,000, and here also 10,000. However, I added two constants that represent the number of samples of both of x and y respectively. I used, as I just said, I used 10,000 before, but now I set these as 1,000. The reason is because since integral with respect to x and y should be dealt separately, it becomes a nested loop. So you can see two for loops. So if I used 10,000 for both loops, I would result in evaluating the summation for 10,000 powered by 2. So that's a very time-consuming process. So I had to reduce the numbers to 1,000, both to 1,000. And here you can see the error is acceptable. Thank you.